Hello dear students, today we are going to discuss about the center of mass of uniform distribution of masses. In other words, we can say we are going to discuss about the center of mass of a system of n number of particles which are distributed uniformly. In your previous class, you would have studied about the center of mass of a two-particle system, and the center of mass whose position coordinate has been obtained as r vector is equal to m1 r1 vector plus m2 r2 vector divided by m1 plus m2. This is the expression what you got for a two-particle system. The same expression is applicable for a system containing n number of particles. So we can use this expression in a more generalized way to describe about the center of mass of a system consisting of n number of particles. So the more general form of the expression for the position coordinate of or position vector of the system containing n number of particles can be given as r vector is equal to sum over I equals 1 to n mi r a vector divided by sum over I equals 1 to n mi. What does this mean? Summation over I equals 1 to n, which means you are taking the product of mass and the position vector of each and every individual particle existing in the system. You are adding up all the products, summing it for all the particles which are running from 1 to n. There are n number of particles. So for first particle, mass is m1, position vector is r1. For second particle, m2, r2. For nth particle, mn, rn. You are just taking a product of all these masses and position vectors, and you are taking a sum and dividing it by the total number of masses. Means n number of masses are there. So you are dividing it by total mass, so that you will be getting the position vector. You would have studied about this in a clear detail in your previous class. I am just explaining. From two-particle system, I am bringing out the same expression for a system containing n number of particles. A system which is said to have n number of particles. And we can say here, this summation I equals 1 to n mi denotes the total mass of the system. Mi refers to mass of the ith particle. The system has n number of particles. This may sound different, but idea is very simple. If there are 10 students in a classroom, all are identical. I am speaking about an individual. I do not know his name, so I can call him I. And then I can speak about some other fellow. Even I can call him also as I. Right? Here, it may create you a confusion that if I mean someone as I, then I have to go as J or K or something like that. If I am denoting a particular person with a notation I, then that indicates the ith person. You can go with A person, B person, C person, up to n persons. There are n number of persons. So you are bringing out everyone into play. In the same way, there are n number of masses. Each and every mass or each and every particle has a mass small m. And then I am speaking about the mass of the ith particle. If ith particle mass is known, if I add all the masses from 1 to n, I will get the total mass of the system. Total mass of all the n particles, total mass of the system, both mean the same. 50 students are there in a classroom, for example. I am speaking about the mass of 50 students. In other words, I can say mass of the classroom. Both are same. Here, I have to mean a class here refers to the students who are existing inside the room. I should not take all the classroom, table, chair, etc. into account. No. What is the mass of the class? In the sense, I have to speak about the mass of the students. So I can say the mass of 50 students, or I can say mass of a classroom. In the same way, mass of n number of particles or mass of the system. Both are one and the same. So I can simply say sum over I equals 1 to n into mi is equal to capital M. Simple. I am getting the total mass here. M is the mass of the individual particle. Mi is the mass of the ith particle. There are so many number of such particles which are running from 1 to n. I may take a value 1, I may take a value 2, I may take a value n. What is the meaning for this? This can be represented like this: m1 plus m2 plus m3 plus m4 and so on up to mn. This is the meaning. This is represented as summation from I equals 1 to n, m into I. This gives you the total mass of the system. So the position vector of the center of mass of the given system can be represented as r vector is equal to sum over I equals 1 to n mi ri vector divided by capital M. Ri vector divided by capital M. So 1 by m into sum over I equals 1 to n mi ri vector. Right. If I am considering the ith particle in a given system, as I am speaking about a system, you should not imagine as you did in the previous section that if two particles are considered, the two particles may lie in a plane, even they can lie in a space also. Here, when you speak about a number of particles and you are speaking about a system, then you have to go for a three-dimensional coordinate system. So I can take x, y and z coordinate system here. Let us consider the system in which you are speaking about the ith particle. This is the point P where the ith particle is present. So xi is the coordinate of the ith particle along the x direction, yi is the coordinate of the ith particle along the y direction, and zi is the coordinate of the ith particle along the z direction. So I can say here xi, yi, zi be the coordinates of the ith particle. These are the coordinates of the ith particle. The position vector of the ith particle r vector can be given as xi I cap plus yi j cap plus zi k cap. This is the position vector. R vector is equal to xi I cap plus yi j cap plus zi k cap. So the position vector is measured from the origin. From the origin, the ith particle is at this particular position. That is denoted by xi I cap plus yi j cap plus zi k cap. What does this mean? Along the x direction, the particle, ith particle is at this particular distance. Along the y direction, it is at a particular distance. Along the z direction, it is at a particular distance. If all the points meet at P, then that gives you the position of the ith particle, which is represented by r vector. That's the meaning. So r vector equals xi I cap plus yi j cap plus zi k cap. This is for the ith particle. See? The system has n number of particles. I am speaking about the position vector of the ith particle. If I am calculating the position vector of the center of mass of the entire system for all the n particles, there is a particular point where the entire mass appears to act. We used to call it the center of mass. So the center of mass of the whole system is somewhere over here. I can call this as capital R vector. What is the difference between small r vector and capital R vector here? Small r vector here denotes the position vector of the ith particle, individual particle at a particular point P. Capital R vector denotes the position vector of center of mass. COM here stands for center of mass. If a ball is taken, if an iron ball is taken, its center of mass lies exactly at the center. So from some origin, if you want to calculate the position vector of the center of mass of the sphere or any other object, irregular shaped object, then I have to use the position vector as r vector, capital R vector, which indicates the position vector of the center of mass of the system, not the particle. It speaks about the whole system, position vector of the whole system. So r vector can be represented as xi cap plus yj cap plus zk cap, where x, y and z are the coordinates of center of mass. See this one? This is the coordinates of small xi, small yi, small zi are the coordinates of the ith particle. Capital X, capital Y, capital Z are the coordinates of the center of mass of the system. Center of mass of the system. So, I can take this as equation number 3, this one as equation number 2, and this one as equation number 1. Substitute for the position vector r vector in this expression 1 and small r vector in the same expression. What will you get? Can write xi cap plus yj cap plus zk cap is equal to 1 divided by m into sum over mi, where I runs from 1 to n, into r vector is xi I cap plus yi j cap plus zi k cap, zi k cap. On comparing these coordinates, I can write capital X is equal to 1 by m into sum over I equals 1 to n mi xi, y equals 1 by m into sum over I equals 1 to n mi ya, z equals 1 by capital M into sum over I equals 1 to n mi zi. So these are the expressions for the coordinates of the center of mass of the system of particles. Coordinates of the center of mass of the system of particles. And in this expression, you can see x equals 1 by m into sum over I equals 1 to n mi xi. As the particles are very finite, atoms and mass, atoms or molecules of this particular system is more in number, it is not at all that much easy to sum up all the masses of individual particles and their respective position vectors. So the product of mass and its position vector, whose sum cannot be taken that much easily. In the sense, we can say the system has more number of atoms and molecules. We cannot do this summation directly. Now, we are going for an approximation. What is that? Instead of considering these atoms and molecules as individual particles, where there is a complication of applying this condition, we are going to manipulate this idea. What is that? Instead of considering single masses of the particles, you consider the entire system is supposed to be made up of so many number of small elements. Small elements. What does that mean? You just consider the n number of particles in a given system is supposed to be made up of. If there are n number of particles over here, all these particles are grouped. You can put it that way. All the particles are grouped into so many number of elements. First, elements in the sense you call it delta m, delta small m. If this is delta small m1, delta small m2, delta small m3, delta small m4, I can take this as delta small m. So I am dividing the entire system into so many number of small elements instead of taking this as particles. What is wrong in this? You can do, but there is a complication because each and every individual particle whose masses cannot be taken into account, because they are of finite size. In a finite system, they are very minute. Atoms and molecules are very much more in number, as you know very well. More number of atoms and molecules are there. So carrying out summation for all such particles may lead to some wrong results. So in order to bring out the exact results, exact approximations, we are going for a different idea. Here comes the essence of the integration. What I am doing is, I am dividing the entire system into so many number of such small elements, each of mass delta m. I am dividing these elements into delta m1, delta m2, up to delta mn. So I have divided the entire system into so many number of small elements. Elements is different from particles. Element is different from particles. So these are all elemental masses. Elemental masses. And we can say now, instead of Mi, I have to replace this as system of particles which are running from I equals 1 to n. So I can rewrite this expression x as x equals 1 by capital M into sum over I equals 1 to n delta Mi into xi. Delta Mi into xi. Here, instead of taking an individual particle, I am taking a system of particles. After taking the system of particles, I am going to mention, or I am going to approximate this into an infinitesimally small element. This element is going to be reduced to an infinitesimally small element. If it is taken infinitesimally small, then that represents the individual particle. When I am going for infinitesimally small particles, delta m get transformed to dm, which is the representation for infinitesimally smaller elements. So x equals 1 by capital M sum over I equals 1 to n delta mi into xi. In the same way, y coordinate is 1 by m into sum over I equals 1 to n delta mi into yi. And then z coordinate is z equals 1 by m sum over I equals 1 to n delta mi into zi. And this representation is the coordinates for the center of mass of the system consisting of these elements. Instead of speaking about particles, I transformed this into elements, the system consisting of elements. And x, y and z are the coordinates of position coordinates along from the x, y and z directions of the center of mass of the elements. System consisting of elements. Now, as n increases, as the particle n increases or n becomes larger, delta m becomes smaller and smaller in size. Delta m becomes smaller. As number of particles becomes more and more, delta m is taken smaller and smaller. If delta m becomes smaller and smaller, this is a very important aspect. You can say here, as you might have studied in differentiation or in a general way, you can say, if you are speaking about a term as delta t tends to become 0, what is the meaning for this? Delta t tends to become 0. The time interval is going to become 0. Interval is going to become an individual number. That's the meaning. Delta t tends to become 0. I can say 5 seconds is an interval. That particular second, instant, that will be obtained only when delta t tends to become 0. In the same way, delta m is becoming smaller and smaller. Smaller and smaller. What will happen? Delta m gets transformed to dm. Summation gets transformed to integration. Summation gets transformed to integration. When will you use summation? When you are adding up intervals. When will you use integration? When you are adding infinitesimally smaller elements. When you add infinitesimally small elements, there comes the integration. So, we can write the same expressions in the form of integration, where x is equal to 1 by m into integral. Integration is taken for all the elements. Actually, this is the summation for all the particles which are running from I equals 1 to n. The summation over I equals 1 to n is transformed to integration. What does this mean? Here you are summing up all the elements which are running from 1 to n. Here you are going to integrate all the infinitesimally small elements which are existing in the same system. The entire element is now considered as infinitesimally smaller elements. Elements are taken infinitesimally smaller elements. Fine elements, very fine elements. So you are going to add all the elements in the given system. All the elements in the given system. Integration is replacing the sum over I equals 1 to n. So x equals 1 by m integral, we can say, what is this delta mi, we can simply write dm. What is this xi? We can take it as small x. Xi becomes x, delta m becomes dm. So capital X equals 1 by m into integral x dm. So this transformation takes place. You can write here sum over delta mi into xi will become integral of x dm. That's the meaning. This gets transformed to x dm. I equals 1 to n. This gets transformed to x dm. In the same way, sum over I equals 1 to n, delta mi, y equals integral y dm. Sum over I equals 1 to n, delta mi, zi gets transformed to integral z dm. So, I can write the coordinates of the center of mass of the system in terms of infinitesimally small elements as capital X equals 1 by m integral x dm. The same way, y equals 1 by m into integral y dm. Z equals 1 by m into integral z dm. So, what I have did? First I have considered individual particles. For those particles, I obtained the expression for the position coordinates from x, y and z axis. Then, instead of taking them as particles where mathematical complication is existing, I am going for elements. And for elements of masses delta m, I have just given out the expressions. Then, I just made an approximation. As the number of particles becomes larger and delta m becomes smaller and smaller, as the element becomes infinitesimally small, summation gets transformed to integration. So I am expressing the same thing in 3 different ways. That's the meaning. For a particle, for an element, and for infinitesimally small element, x equals 1 by m into integral x dm. You can say integral of x dm divided by capital M. That's the meaning. Y equals 1 by m into integral y dm. Z equals 1 by m into integral of z dm. These are all the coordinates from x, y, or position coordinates from x, y and z. In general, the position coordinate of the center of mass of the entire system from the origin can be represented as r vector. I can write this here. R vector is equal to, because the right hand term in this expression, you just look at this, the right hand term in this expression is in terms of vector. So I have to represent once again the position coordinate in terms of vector. So r vector is equal to 1 by capital M into integral of r vector dm. R vector dm. This is the representation. Capital R vector equals 1 by m into integral of small r vector dm. So that I will get the position vector of the center of mass of the system of particles. Now, this is the vector form of, or the vector expression of all these scalar expressions. Now, I can conclude, or I can say, if the center of mass lies exactly at the origin, center of mass of the entire system lies exactly at the origin, then this term goes to 0, or this becomes 0. Then this integration becomes 0. That is, integral of r vector dot dm will be equal to 0. In other words, I can say integral of x dm, integral of y dm, integral of z dm. These are all equivalent to 0. When the center of mass lies exactly at the center, at the origin, then the position vector is equal to 0. So the expressions can be r vector equals 0, or integral r vector dot dm equals 0, or integral x dm equals, integral y dm equals, integral z dm equals 0. This is all about the center of mass of uniform distribution of masses, or the center of mass of system of n number of particles. Let us now discuss an example problem which is related to the center of mass of a system. Look at the center of mass of a uniform rod of mass m and length L. Now, to calculate this, let us consider a uniform rod. What does the term uniform mean here? Its area of cross section remains same everywhere. We call it a uniform rod. So, a uniform rod of mass capital M and length L is taken. One end of the rod is is there at the origin, and the rod is lying on the x direction. In order to calculate the center of mass of the uniform rod, we are going to assume a small element of mass dm whose elemental length is dx, which is at a distance x from the origin. Which is at a distance x from the origin. I am assuming a small element of mass dm, elemental mass is dm, and a small element, infinitesimally small element. That's the meaning. This is infinitesimal. Whenever I write dm, then that denotes, when I say element, that means infinitesimally small element. So dm is the infinitesimally small element of length dx, which is at a distance x from the origin. Which is at a distance x from the origin. Now, let us say lambda be the linear mass density, which is mass per unit length. Mass per unit length. We call it linear mass density. Lambda is the linear mass density, which is mass per unit length. If for unit length mass is taken to be capital M, whose representation is lambda, what is the mass of the small element of length dx? For a length L, mass is taken as capital M. For length dx, what is the mass? We already saw it is dm. What is the measure here? What is dm here? I can simply write m divided by L into dx. M divided by L into dx. Right? You can simply say a chocolate costs 1 rupee. What is the cost of 10 chocolates? Multiply by 10. What is the cost of half a chocolate? Multiply by 0.5. For 1 meter length, mass is capital M. That is mass per unit length or linear mass density. If linear mass density is lambda, you can say in other words lambda into dx. If linear mass density is lambda, then what is the mass for the length dx? Multiplied with that length. Dx is the length. So lambda multiplied with the dx will give you the mass of that particular length alone. So m by L is the linear mass density. Multiplied with the dx will give you the mass dm. Now you have to calculate the center of mass, position of center of mass. You are asked to locate the center of mass, position of center of mass. So as the rod is placed along the x-axis, we have to go for the expression xcm is equal to integral of x dm divided by integral of dm. Integral of x dm divided by integral of dm. This will give you the position of center of mass of this uniform rod lying along the x direction. And we can say here integral of dm, as we saw earlier, is simply capital M. So I am taking 1 by integral of dm as 1 by m itself. This is integration between the limit 0 to L x dm. Integral 0 to L x dm, because I have taken a small element of length dx. If I add so many number of such small elements of length dx from 0 to L, I will get the total length L, whose center of mass can be determined. Whose center of mass can be determined. So I am running from 0 to L into x dm, integral 0 to L x dm. So 1 by m is there. Integral 0 to L x is as it is. What is dm? We saw m by L into dx. You can write m by L into dx. M by L can be taken out. M by L can be taken out. So this will be equal to 1 by capital M into m by L into m by L into integral 0 to L x dx. Integral 0 to L x dx. This is the expression for the position of center of mass of a uniform rod of length L. This m gets cancels out, so you will have 1 by L. Integral of x dx is x square by 2. X square by 2 between the limit 0 to L. Substitute upper limit and lower limit. 2 can be taken out. So you will have L square minus of 0 square This is 0, so L square, L gets cancels out. We'll have simply L divided by 2. So the position of center of mass of a uniform rod of length L lies exactly at the center of the rod, exactly lies at the middle of the rod. X is equal to L divided by 2. If length L is 10 centimeter, the position of center of mass lies exactly at 5 centimeter. You are given 30 centimeter scale, where the position of center of mass can be found exactly at 15 centimeter. For a 30 centimeter long scale, the position of center of mass lies exactly at 15 centimeter. For a 1 meter long scale, the position of center of mass lies exactly at 50 centimeter. So XCM is equal to L by 2, which means if you consider the scale or consider the rod along the y direction, once again you will get YCM is equal to L divided by L by 2. ZCM is equal to L by 2. Means whatever the position in which the scale is placed or the rod is placed, the position of its center of mass lies exactly at its center at a distance of L by 2. So this is an important result. You will be asked with this question. This is, you are going to tabulate the positions of center of mass of different shapes, where this comes first. What is the position of center of mass of a uniform rod of length L? The position of center of mass lies exactly at midway of or at the center of the rod of length L. That's all about the measure of center of mass of the distribution of uniform distribution of masses or a number of particles and an example related to it. Thank you.